Okay, in yesterday's class, we learned about big O, big omega, and big theta, um, um, ways of representing the complexity of programs. We also learned about the sum and product rules for algorithm analysis. And we also learned how to analyze recursive functions. Okay, so now today what I'm going to do is I'm going to take, let's try rewrite this recursive sum that we did yesterday. Int n, and if n equals 0, then return 0, else return n plus recursive sum of n minus 1 plus, oh, this is what we had written yesterday, so I'll keep this here and end module. Today, I'm going to write a slightly different variant of this recursive function, f module recursive sum int n again. If n equals 0, then return 0, else return n plus recursive of, let me call it E over here, recursive E of, recursive sum E of n minus 1, slightly extended version, plus recursive sum E of n minus 1. Let's say this is the new program that I'm writing, end module. So this program, we saw that the complexity was order n. Let's look at this function and see what this one's complexity will be. So the heart of the recursive function, as we saw, is the recurrence equation. So let's say this computation, which is the addition of three terms, is cos u sum c over here, and this comparison and this return cos u sum d over here, just like yesterday. But what do we have here? We said t of n, the cost of c, plus 2t of n minus 1 is this new recurrence that we're going to have. And we'll have t of 1 equal to sum d. So what we do is, let's try and expand this recursion. C plus 2t of n minus 1. Let us take, I'm sorry, not t of 1, this should be t of 0 over here. Okay. And let's say n is equal to 3. Okay. So I have here t of 3 equals c plus 2t of 2. T of 2 is equal to c plus 2t of 1. And t of 1 equal to c plus 2t of 0, and t of 0 equal to d, and that is when the recursion stops. So let's expand this t of n in terms of these values. I'm assuming that n is equal to 3, right? So I have t of 3 is equal to c plus 2 into c plus 2 into c plus 2 into d, right? This is the um, cost for computing t of 3. Okay, so let us see how many c's are there in this. We have t of c is equal to 2 to the power of 0 into c. I'm just slightly writing it differently. 2 to the power of 1 into c plus 2 to the power of 2 into c plus 2 to the power of 1 into c 2 to the power of 3 into d. This is the total number of c's that are there. And let us say I take some c naught equal to max of c comma d. Then I can write t of 3 is less than or equal to 2 to the power of c plus c naught 2 to the power of 1 c naught plus 2 to the power of 2 c naught plus 2 to the power of 3 c naught. So now what is the sum now? What is the total number of c's that are there? We'll find that t to 2 to the power of 3 is less than or equal to 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 into c naught. So t to the power of 3 is less than or equal to 1 minus 2 to the power of 3 by 1 minus 2 to the power of 4, sorry. And this is equal to 2 to the power of 4 minus 1. Or for T3, we need how many operations? 15 calls to the function. That means the code in the function is repeated 15 times. Okay. So when I look at this equation over here, and I can generalize this and say t of n is equal to 2 to the power of n plus 1 minus 1, or in terms is less than or equal to, sorry here, or t of n is equal to big O of 2 to the n. So it takes exponential time complexity. Okay, so this is something that we must be very aware of. We should notice that something as simple as adding one more recurrence can make your algorithm, which was originally linear, become exponential. Okay, so this is something that we need to worry about. All right, so now the question is, sometimes recurrences can become very difficult, and in your algorithms course you will learn what is called a master theorem, which will help you solve recurrences. But you can wait for the algorithms course for that. Here, on the other hand, I want to show you one simple method, which is a foolproof method. In fact, the master theorem also fails sometimes, and this is what is suggested. So let us look at recurrence of, let's look at this recurrence over here. We are looking at recurrence of, so we started out with n. This becomes 2, it branches out, creates two, functions n minus 1. This creates two functions n minus 2, n minus 2, n minus 2. This And what happened? Okay. So what happens is this started off with 2 to the power of 0. It doubles, becomes 2 to the power of 1. Here it again doubles, becomes 2 to the power of 2, and so on. And finally, you have t of 1, some t of 1 somewhere. And this t of 1 again splits into t of 0 and t of 0 and so on. So notice that from one level of this tree to the second level of the tree, it continuously keeps on doubling. Okay. But what you have to do is you can easily write this for any recursive function. You can write like this, see how many times it's getting called, and just count the number of nodes in the tree, and this will give you the time complexity of the algorithm. This is the easiest way to solve. You have to write the recurrence equation. If you have any difficulty in finding out what's the actual time complexity, you simply do accounting using a recursion tree. Okay. So we have looked at, as I said, some rule, product rule, and so on. We will take finally one example where we do all the stuff. Before that, there are other things that I want to talk about. For numbers, for example, we compute complexity in a slightly different way. For example, when we say input size, when I'm looking at sorting or searching, it is the size of the array. We look at the size of the array. Whereas, let's say when I'm doing prime classification, or I'm doing factorial computation, the time complexity is computed differently. What we do is, if you want to find whether a given number is prime, what? It's basically how many digits it takes to write this number. So you take log of n to the base 10, and this will be 4. We say that a solution is linear only if it takes 4 units of time. It's not the up to, you cannot go up to 1941, which is your standard algorithm for prime classification, for example, which gave you the solution in terms of linear time. Here we are talking about the number of places in the given number. For both prime classification and factorial computation, you count by the number of digits it takes to write a given number. So if you want to say that something is linear, let's say I'm doing prime classification of this, and I want to say that the solution is linear, that means it takes 6 units of time. Okay. This is beyond the scope of this particular course. You will learn various algorithms which look at the size. So we'll stop here, this particular topic, and we'll come back to